Let's see here. Okay. Hello, everyone. Can everyone hear me? Great. Okay, cool. So today I'll be giving a group theory lecture. I will be covering, so we'll be covering the book, right? The book. Michael Artin, our Algebra will be doing the end of chapter 2. That's where Rand's finished off. We'll be talking mainly today. So the lecture is supposed to start at 8, it's a bit 10, it's fine. Um, we'll be talking about, so here I made a resume of what we'll be talking about. Yeah, so we're going to give a review on equivalence relations just to get a fresh reminder because those are going to be useful for cosets. We're going to talk about how cosets are just equivalence classes. We're going to also talk about a function that arises oftentimes when we consider equivalence, like cosets, and in general, equivalence relations called the canonical surjection. We often do it by. Then we're going to give an application of these cosets in modular arithmetic. So that will be section 7 of the book. To finish off, we'll be talking about quotient groups. So yeah, cosets can form a group under certain conditions, namely when they are normal subgroups, a topic you may have encountered before, but I will be giving a reminder on. And if there is time towards the end of the lecture, I will be giving the first isomorphism theorem. I might, if I have time, I might prove it, but I would rather just give it and do applications. So this kind of goes back to the beginning of the lecture. I just had a few notes I wanted to say. So like active listening is definitely encouraged. I mean, you do math, it's definitely not a spectator sport. Um, there are no formulas. There are no formulas in the sense that you don't like just apply stuff um, out of memory. You try and understand the material as best as possible, and that kind of leads me to the third point, where you should definitely, when I, a way of learning math that has helped me a lot is by prioritizing overview before detail. You want to have the general understanding of the landscape you're working in. So, for example, group theory, before just diving into the proofs. Well, diving into the simple proofs is important, but you shouldn't waste time on the details. Anyway, so I will just be talking about that. We start with equivalence relation. So this is section 5 of the book. All right, what are equivalence relation? So fundamental mathematical construction is to start with a set S and to form a new set by equating certain elements of S according to a given rule. Okay, so we may call this rule twiddle. Twiddle will basically be a subset of the set S cross S. Why is this? So uh, to be able to equate two elements, I don't know, say A is equivalent to B, I will be taking an input. So here I'll be taking an element from S and another element from S, and I will be creating a certain rule on the set S. So basically, it's kind of like a set is something with zero structure. I'm adding a certain structure to it via a relation. So we have a lot of relations in math, and in particular, the equivalence relation is the most important. So how can an equivalence relation really be thought of? So to begin, I will be giving, so let's consider a set S. I will be considering a partition of the set, so we call it P. And what is a partition? It is basically so if I have a set S, all right, so these are elements you can imagine, all right, of any nature you like. A partition basically is, first of all, it's a covering of the set, so it's a set of subsets, to kind of, I guess, which cover the set evenly in the sense that there are no overlapping between each parts of the equivalence classes, but mainly the most important is that it covers the whole set, right? So here it's kind of, you can kind of think of it as different cells, right? You either live in one cell, you either live in one cell, but you can't live in two at the same time, and every cell covers the whole set S. So this is an example of a partition. Partition, so it's a disjoint union of non-empty subsets. It means we can write S as, if we call the set A, A1, A2, etc. We can write A1 disjoint union A2 disjoint union A3, etc., and we recover the whole set S. So that's a really important thing. Uh, and now let's dive into an example. Okay, so I just gave a definition of the partition, right? Maybe we mean a subdivision of S into non-overlapping subsets. I won't be writing the full definition. So let's just focus now on the first kind of relation. So this is the only one we'll be studying today. It's just a quick review. Equivalence relations under the set S for, so if we consider on the set S. So what are an equivalence relation? So an equivalence relation, well, in a more axiomatic way, it requires you to be first transitive, then you need to be symmetric. So transitive means that if A is related to B and B is related to C, then that implies A is related to C. Symmetric is simply a way of saying that if A is related to B, then that is if only if B is related to A. And thirdly, reflexivity, which is the most basic one, it simply says that A is related to A. So here, this is just basically the axioms for a definition of an equivalence relation. How can you see it? Well, it's really simple. What an equivalence relation is telling you is what are the commonalities between each point. Okay, so for example, I don't know, say we have, let's define a set of objects, right? For example, uh, pentagon, I have a circle, I have another pentagon, but maybe now it's like shaded a bit. I have another circle, but now it's kind of shaded another way. And what I'm saying is that if this is my set S, right, an equivalence relation possible could be, oh, they have the same shape, right? So if the circle and the shaded circle would be both related because they have a commonality. That's the fact that they are both circles. I could also have then the pentagon and the shaded pentagon would be equivalent. And we could also define a different kind of relation now. We could define a relation on whether the shapes are shaded or not. So for example, here I could say, okay, the circle is related to the pentagon because it's not shaded. That's one commonality. And the shaded circle is related to the shaded pentagon, obviously, because shadiness is also a certain trait that is shared between both objects. So you really need to think of equivalence relation as basically saying, okay, I'm giving a statement on a certain trait that is shared between different objects, and this trait can be in turns can partition the whole set, right? Because you can't have this if an object has a certain trait, it can't have the other traits, right? So that kind of explains the non-overlapping nature. So yes, so you may have hinted now, okay, so partition is not correctly written. Equivalence relation partition the set, but how, right? So let's quickly dive now into equivalence classes, and this is a really important part of equivalence relations. So what is an equivalence class? So it's denoted CA, and we'll be writing it as, I don't know, yes, so it's the set of B's belonging to S such that A is related to B. Great. So we defined, and now we defined a relation, a twiddle on the subset of S cross S, because right, you're giving a relation between two elements in S cross S. And one element technically in S cross S, but you're having one element in S, another element in S. That's what this notation means. And so now the equivalence class of CA, right? So it's the B going to S such that A is related to B. Well, that just forms a partition. Sorry. Yeah, that forms a partition. How can we see that? Well, if I have a set S now and I'm considering several different objects, all the elements which are in CA, so first of all, by definition of the equivalence relation, A belongs to CA, right? Second of all, we're going to have that any element which is related to A by definition would be in the equivalence class. And we would see that eventually all the elements which are in relation to A would definitely uh, cover a certain part of A, and if we considered other representatives, so if we took, so this is one representative, possibly, but if we had another B, then we would have that CB is actually equal to CA, right? Because now if you're considering, you can just use transitivity to show this. If you're considering another element in the set in the same equivalence class, it's going to be representing the same equivalence class overall because they have the same property, right? The same property that is denoted by twiddle. Right? So one property is that if, so this is property 5.4 in the book. So if CA and CB have an element D in common, right? So D belongs to CA and D belongs to CB, then that implies that CA equals CB. I won't be proving this, that we're just doing a quick review on equivalence relations. It's really not that hard. I even encourage you to do it. Otherwise, other than that, so now we have basically the groundwork for equivalence relations. Let's talk a bit about an object we call a canonical surjection. So we're taking a set S and we're sending it to its class of representatives. Okay, so what does this do? This map, so we call it the canonical surjection because every element must be related to itself at most. So you're going to have an I don't how Americans say it. Well, it's just surjective basically. Um, what this map does, it kind of sends all elements of a set, right? So I have an element A, and I'm sending it to its equivalence class. So, for example, here's well, how do they define it? Yeah, we're just going to send it to an object called a bar. A bar is the element, kind of the representative. Sorry, the representative of the set S. What does this mean? Okay, let's just try and understand this. So if you have a set S, right, and you can partition it into different elements into different equivalence classes via a relation denoted twiddle. So for example, I have a representative here called A, A1, A2, A3, and A4. I can map this now into the set S bar. S bar would denote, basically, it's kind of like you can think of it if you can denote each property related in a set. So if A1 shares a certain property in common with another element in its equivalence class A1 tilde, um, what we can do is send it, we can say that's a property, okay? So for example, in last example, it was shadiness. We can send it to a certain category. So we can say that now this is basically, if this is the equivalence class of A, I can send it to the element a bar, and a bar just denotes what's the commonality between all elements in the equivalence class of A. And this is just a way of shortening it. So I can do the same for a2 bar, a3 bar, etc., a4 bar. Great. So let's continue. This is the canonical surjection. It's not very well, I haven't really well defined it. Mm, Basically you can just think of it as you have a bunch of elements uh, in each equivalence class, and to shorten it, you can just send everything to a shortcut, right? A3 can represent everyone in this equivalence class. A4 can represent everyone in this equivalence class without having to repeat all the redundancy in a certain way. Okay, great. So for example, I mean, a quick example. So if you have a canonical surjection, you can just imagine, uh, we could imagine Z being sent to the even and odd integers. And so here I let you guess what the equivalence class would be. Well, it would be either your odd, either your even. So mod 2 if you're 0 or 1. This would define a canonical surjection because you're basically sending each integer to what equivalence class it is. So the equivalence would be A is related to B if and only if A equals B mod 2, right? So mod 2. So if they have the same remainder under uh, Euclidean division by two. Great. So we can now continue. Let's see. I just want to continue now. I don't know if we have a lot of time. Yes, okay. We're going to continue with a proposition. So, actually, not a proposition, sorry. Basically, yeah, so to clear up the notation before it's used in the book, A bar equals B bar is just another way of saying that A is related to B, right? And so that's kind of obvious from the context. So we're kind of removing the redundancy in each equivalence class. We're using one representative for each category. So category in the sense equivalence class. Great. So let's continue now. I'm just going to talk about fibers, right? So basically, so any map phi, so if I have a map phi from a set S to T, defines an equivalence relation on the domain S, namely the relation given by the rule A is related to B if 5A equals 5B. So this is kind of so in the book they refer to this as the equivalence relation determined by the map. So why would this be a relation? Let's see. If we have two elements that are so imagine I have a set S, right? I have two elements A and B. They're both mapped to the same element in a set T. So here we'll call it Y, right? We just need to check if this is an equivalence relation. So this is a bit routine, but I will do it quickly. So obviously A is related to A. Obviously A is related to B, and B is related to A, right? So symmetry is definitely guaranteed. And transitivity is really quite easy also. So if I have A related to B and B related to A, which simply means that 5A equals 5B, and 5B, yeah, sorry. The third element C, 5B equals 5C, then obviously 5A equals 5C, and thus A is related to C. So this allows us another way to build an equivalence relation. The corresponding partition is made up of the non-empty inverse images of the elements of T. Right? So by definition, the inverse image of an element T is the subset S consisting of all elements S such that 5S equals T. So you can think of it as phi inverse of some element in T, right? So we can take Y in this case. Phi inverse of Y is simply the set of S belonging to capital S such that phi of S equals Y. In particular, because this is the singleton, right? So, and here, what we can think of is that this is kind of like the canonical surjection we thought of before. Well, given the phi as a surjection, obviously, but well, really here we would have to write the image of phi, but suppose that the map phi is a surjection, okay? So that means every fiber, every one of these sets for each y and t is non-empty. What we can think of is that these five t's, they represent basically different pockets in the set S, which all send elements to y, right? And these elements, they define precisely a certain equivalence relation, and that's the one determined by the map phi. Okay, and of course, well, this adds the condition that phi is surjective. So really, we would have to think of, if we wanted the real canonical surjection, we would think of the set of elements S which send it to the image of phi. So each element S would be sent to well, obviously 5S, but here no elements would be missed, so the equivalence classes would be non-empty, in particular the fibers. Great. So let's continue. We're going to hop on to proposition 5.13. 5.13 just states that if I have a map 5 from G to G prime, and it's a group homomorphism with kernel n, so let's write it down. Kernel of phi equals n, and AB are elements of G. That implies that 5A equals 5B if and only if b equals an for some element. There is, so let me write it properly. So this implication means we have the equivalence. There exists an n belonging to capital N such that a, well, yeah, a equals bn. Same thing. Great. What does this mean? So if I have a group homomorphism and the kernel is phi is n, so we recall what that is, I suppose, previous lectures. Then we have that 5a equals 5b, if and only if we can basically rewrite a as some multiplication of an element in n. And so this is really not very hard to prove. We're going to start, so begin by supposing, so we're going to start with the first implication. We suppose the kernel of phi is n. If 5a equals 5b, in particular, I can rewrite this as 5a phi of b inverse equals the identity. In particular, 5ab inverse equals the identity. But obviously, all elements which send to the identity via phi are elements of the kernel, which in particular is n. So this belongs to n. And so AB inverse belongs to n, implying there exists an n belonging to capital N such that A equals B. Great. And so for the other implication, well, the other implication is really easy. If there exists an n such that A equals Bn, right? Since the map is well defined, I can simply just take the phi on each sides. And in particular, by the property of homomorphisms, I can say 5b, 5n equals 5b, and that proves the statement. Great. So what really is the point of this? Well, if we look at the map phi, and we look at it from the perspective of G, a set, so a group in particular, sorry, and the map G prime, if the kernel of f of phi is this little subgroup, well, we denote it n, but yeah, it's a subgroup. And we look at all the elements such that 5a equals 5b, well, we kind of see that they must basically A inverse B must be in the kernel. So let's continue on. Right. We're going to end up with a corollary. So on group homomorphisms, 5.16. A group homomorphism phi, so phi from J to G prime, is injective if and only if the kernel, yeah, so the kernel of phi is the trivial group. Great. So let's begin with the proof. We're going to start by the first implication. So we suppose phi is injective. And we need to prove the kernel is trivial. Great. So if we have that phi is injective, in particular, I can write down 5x equals 5y implies that, so hold on, 5x equals 5y implies that x equals y, right? You can start by saying that 5 of x, phi of y inverse equals e, so 5xy inverse equals the identity. I thus say that, so I know this statement is true for every x and y. If I consider beginning of my statement, so 5x, 5y inverse equals e, that means that xy inverse belongs to the kernel. Okay, actually, hold on. Let's start with the other implication. Okay, let's start with the other implication. This will be maybe a little easier. Okay, so we start with the kernel of phi equals e, and we need to show. We suppose then that 5x equals 5y, and we show that x equals y. Okay, this is gonna be easier. So 5xy inverse equals the identity, right? So we're supposing that 5x equals 5y to show that x equals y. If 5xy inverse equals e, that implies that xy inverse must belong to the kernel, but in particular we know the kernel is trivial, so xy must be equal to e. Xy inverse must be equal to e, so x equals y. Great. I'll leave the other direction for as an exercise. I think it's pretty easy. Just start by saying, so if you want to show the kernel of phi equals the identity, you're going to suppose start by saying that if this is true for every x and y, right, 5x equals 5y, then I can just say, great, so if I choose y to be the identity, I can say that phi of x equals the identity, and that implies that x must be also the identity. Great. Um, let's continue. Six cosets, right? So we're going to start with cosets. Cosets are a really important part of groups because they enable us to basically, like equivalence relations, partition the group into different kind of cells, right? So the way we can see cosets is if I have a group G and I'm considering a certain subgroup, okay, actually it need not be a subgroup. Um, sorry, no, it does need to be a subgroup. So if we consider H to be certain subgroup of G, right? Let's know it here. Then we can basically partition the group H into several cells of the set G. So we can imagine this is AH, maybe BH, and then it ends with CH. And all the cosets are going to partition the group. So this is the motivation. So now let's try and introduce this better. So if I have a subgroup H of G, and I'm trying to consider a coset, so A times capital H. A times capital H is basically the set of all AH where H belongs to capital H. And this is for some element A belonging to G. So the most important thing to remember is that these cosets, these individual cosets, they do not form a group. This is easy to see because the element, the identity itself does not belong to AH, right? So we continue on. So AH belongs to G. Um, basically being in a coset, so if we define this equivalence relation now on the group, on the set G cross G, and I say two elements, okay, I now say that two elements are related, A is related to B, if and only if two elements are in the same coset. So if AH equals BH. And in fact, this this creates an equivalence relation, and this is extremely important for the rest of the lecture because what this means is that I can make the group G into separate different cells, and this will help us, for example, prove Lagrange's theorem. Let's just show now. So the statement is that this this equivalence relation is an equivalence relation, so it's just proven. So obviously, symmetry, so sorry, reflexivity is definitely easy. Transitivity is, I mean, this is just equality of sets, right? And same goes for, so hold on, let's just do transitivity. A is related to B and B is related to C, so we have that AH equals BH and BH equals CH, and obviously this implies AH equals CH. Great. Let's see here. Okay, here they don't prove it quite the same way. I mean, it really is the same proof. Uh, sometimes when you're unpacking, when you're solving group theory problems, it is better to unpack cosets. So if I want to say that's, okay, let's maybe redo the transitivity one. If I want to say that um, A is related to B and B is related to C, this basically means that I can write A as a BH and C as another B. Also, let's write rather C equals B H prime, right? This says B equals AH. And this is for some H belonging to capital H and some H prime. So these are two basically arbitrary elements in H. if I can say that A is related to B, so A is in the same coset as B, and B is in the same coset as C, I can just write these two equivalents to these two equalities. What this leads me to by simple injection is that by injecting the equation, I can simply say that um, C equals, so since B equals AH, I can just write AH, so hold on, AH H prime, right? And so since this is also an element of H by the fact that H is a subgroup, I can simply say that C is related to. So yeah, so it does come off as pretty natural that these would form an equivalence relation. In fact, since they form an equivalence relation, we can even say that they partition the group, right? By definition. So this is great. They partition the group. I can now even say that if, as an extension of the previous lemma we used on equivalence relation, if two cosets A and so if two elements are in the same coset, and sorry, so if D is an element of AH inter BH, right? So there is an element in these two cosets for A and B arbitrary in G that automatically implies that AH equals BH. That's great. So, so we can definitely give quite a lot of examples. I will just, there's one example I like often because it's really quite visual. We can, for
Um,
example,
s-
consider
Sorry, Goose. So we're coming up on closing time. So unless you have a really quick example, there's a question from chat that I'd like to bring to your attention. But let me know what your plan is.
yeah, yeah, sorry. Coming up
Uh,
to time, I thought there
y-
was another hour.
there is, but the Zoom meetings can only go 40 minutes at a time. So we'll
Okay.
need to remake afterwards.
What,
Um,
what's the question?
okay. Yes, you can also read it.
Oh, sorry. Yeah. What what
Can
platform
you
is
go
it
back
on?
to the previous slide, please?
Oh yeah, yeah. Oh,
So
sorry.
in that upper half of
I,
the screen, you write that A is equivalent to B if AH is equal to BH. But
mhm.
then when you're writing down this statement, it's you have uh, you write like B is equal to AH. So can you say a word about the difference between those? Like maybe I would expect
Yeah,
that to say
yeah, yeah.
like AH is equal to BH prime.
Yeah, you're right. So when we say that two cosets are equal, right? We're not saying basically um, you can think of H. So let's think of H as a list of elements. So H1, H2. Okay, all the way. Maybe let's say it's a finite group, right? So it's H all the way to Hn. When we're saying that two cosets are equal, and so basically you're rewriting the set as I'll write it vertically. Okay, so it makes it more clear. A1, so sorry, A H1, right? So you're multiplying the first element, A H2, the second element, you're going all the way down to AHN, right? And now you're doing the same step for BH. So BH1, BH2, all the way to maybe some BH, so BHN, right? The last element. So this is a left coset AH, BH. And what I'm saying is that when two cosets are equal, it doesn't necessarily mean that AH1 is equal to BH1. It just means that there's a bijection between these two sets. So, for example, when I say this set is equal to this set, it means there is a corresponding other index, right? So such that AH1 is equal to some BHJ, right? And by saying this statement, right? So if AH equals BH, I'm basically saying that there exists, and for some index I, there's another index J, such that AHI equals BHJ, right? But now, okay, if I can say this, I can definitely say that A equals B HJ HI inverse. And since this is a group, I can just contract this to some other element H, and I can say that A equals BH. So this is kind of, and it really works in the other way. I mean, here you just need to multiply on the right by H inverse, and then you can just relabel H inverse as H. And so that's kind of explains why you can say that, sorry, wrong slide. That kind of explains why you can just contract this statement into this one. Is that clear? I
Excellent.
hope.
Well, Hamza, feel free to tell us in the Discord, but for now, I think we should wrap. Um,
Okay, yep.
Feel free to everyone to stand up and stretch, take a few minutes of break, and we'll see you back in about 10 minutes when we'll continue talking about examples of cosines.
Yep. Good.
Thank you. Bye.
So we're gonna start. We left off with cosets, and so now I'm just gonna give you some examples, right? So let's begin with something simple, right? So we're gonna start with the group C. So the group C of integers under addition. And consider this group, and we're going to consider all cosets. So let's see. If we have a group C, and then I look maybe at 1 plus C, what this basically does is, if I have the think of if I have the line of integers, all lattice points here, I am basically saying I'm shifting everything to the right. Well, here it doesn't really have much interest because basically translating everything to the right just gives the same thing, the integers. So particular 1 plus C is just C. And why is this? Well, we'll see later on that this is because 1 is just an element of Z. So any element in particular, if I have H times capital H, and H is a subgroup of G, so here we just consider a general case, then this is just the group H itself, right? Maybe if I consider another example, let's see, we can choose something a little different. We can maybe say, we haven't done modular arithmetic yet, but I will just introduce it as a cyclic group. So let's say maybe Z over 10Z, right? And we're going to endow it with addition. Now it's going to be modular. We're going to show this later, but right now it's just going to be graphical. So if I imagine now a line and I have 10 lattice points, so I start with at 0 and I end at 9, I'm going to have 1, 2, etc., all the way maybe to 8, and then it's 9. What does it mean to have cosets here? Well, if we just do the same thing and we consider the whole group, then obviously we wouldn't have a very interesting example. So what we're going to do is we're going to consider the cyclic subgroup generated by 2. And so what this does is it basically, so I'm going to just, I draw, I'm not counting here, so it's probably not 10. But anyway, I'm just saying, basically, I'm jumping from 2 to 2, right? And what I'm saying is that this is also a subgroup of G. So now what does it mean to consider a coset of this subgroup, which is a subgroup generated by 2? Well, it simply means if I have 0 plus 2, well, that's just 2 itself, right? Because I haven't shifted anything. But if I consider 1 plus this group, okay, now I'm basically looking at this set. I am basically shifting everything by 1. And this is a coset. And what do we notice? Well, if I have 2 now plus this thing, well, 2 is just basically an element of this cyclic subgroup. So this is just basically equal to 2 itself. And so we've basically kind of created this map of all cosets of this for this particular group. And so what does this mean? Well, we had a lemma. We know that being in the same cosets, so in particular A related to B if and only if A capital H equals B capital H, we know this defines an equivalence relation. And so in particular, it means that all the cosets, right? Each coset corresponds to an equivalence class. So if I have a set here, equivalence class, and all the equivalence classes, so this is one, for example, they partition the whole set. And so in particular here, they partition the whole group, and we can see this because if we look at the cyclic subgroup generated by 2, so this is this one, this one, this one, etc., going all the way by pairs of 2. And now I consider the other coset, the only other existing one, by the way, 1, 3, etc., etc., etc. And I just kind of make this disjoint union. So I have 2, and I take the disjoint union of 1 plus 2, right? So this 1 plus generated by 2. Well, this is basically the whole group, Z over 10Z. So yeah, these are a few examples. You can definitely create more. You could, for example, look at the cyclic group, this for the permutation group, and look at it under composition. If we look at this group, we can definitely create some cool examples. One such example would be considering, for example, all the cosets of the form. So we take a subgroup, so we can maybe take a subgroup generated by the permutation 1, 2, 3, and we would multiply it by some element, right? So we can maybe take some element G, and all these elements for all the G's would create a partition for the group Sn. And obviously, well, there would be some that would repeat, right? So they would be in the same equivalence class. So we would remove the redundancy, basically. If I draw a picture, if this is maybe some G, and we have a subgroup, so this is the subgroup generated by the permutation 1, 2, 3, then all the cosets, they form this kind of neat little pavement of the group. And in particular, G times this would be living, so the representative, I'll denote it by the bar. The representative, the equivalence class would be living here. And so if I had some other element, I don't know, F, its equivalence class would be sitting here, and all the other elements would be in the same equivalence class under being in the same coset. Great. So now we have this kind of view of how cosets are just equivalence classes, and being in the same cosets in equivalence relations. So now we can kind of define the most important theorem, which is called Lagrange's theorem. Lagrange's theorem. Lagrange's theorem is a statement, so I'm just going to quickly describe it. Maybe you guys can guess a proof in advance. So if I have a group, we can start off group G with finite cardinality, and I have some subgroup of G, then that must imply that the cardinality of H divides the cardinality of G. What this means is that basically the cardinality of G is a multiple of the cardinality of H. So how are we going to prove this? This is a really cool statement because it lets us prove a lot of things in group theory. There's actually, when you advance furthermore, you might even be able to find a converse of this. These are given by the Sylow theorems, but that's something for another day. Let's just start with the proof. So for this proof, right, we're going to start off by stating something, is that we're going to show that basically the cardinality of H equals the cardinality of AH for A not belonging to H, right? So it's not trivial. Right? If A belonged to H, then obviously H is equal to AH, so they have the same cardinality. But what we want to show, so this is a quick lemma, is that these two cardinalities match, and we're going to do this by creating a bijection. So let's create a bijection. We're going to send H to AH, and this will simply be done by multiplying the left element, so an element H, by to the left by A, for some A not belonging to H. So let's first of all check this is well defined. So if I have H1, this is always a crucial step, so I'm giving a good tip when you're solving group theory problems. You always need to check the function well defined. This is really important. This is a mistake a lot of students make because they create a function, they think it's great, but it's actually not well defined, so it's not even a function, right? So how can I simply prove that this is well defined? Well, I just need to multiply both sides by A on the left. This is, of course, something we're allowed to do with groups. If I have AH1 equals to AH2, then obviously if H1 equals H2, so I'm well defined. If I do the inverse now, because of the left cancellation law, I can say that for AH1 and AH2, I can cancel both sides. So I actually have the inverse relation, right? So I have not only shown well-definedness, but actually injectivity. So that's great. Let's just show now surjectivity. So let's begin by saying I have an element G belonging to AH. That means that G can be written as some combination, right? So A times some H1. Well, the obvious choice will just be to choose the element H1 in H to be the map, right? So where psi of H1 will precisely be AH1, which equals G, which proves surjectivity. So this is a bijective map. That's great. Not very hard to prove. Now we're going to use another fact. So if we are in the same coset, in particular, we form a partition. Right? So lemma. Same coset, so induces a partition, like we showed before. And this means in particular that if I have the cardinality of G, I can write it as the sum of the cardinalities of all the cosets. So this is really easy to see, right? If I have different cells that basically compose this kind of like potato shape set S, right? I can kind of see that, oh, okay, if I have this many elements here, this many elements here, etc., and I just kind of add them all respectively given each equivalence class, I basically sum up to the whole set. This is because the equivalence class of being in the same coset, so AAG equals BH, this induces a partition of the set S. So I can write that for each representative, so A rep, right? So I don't, basically one mistake I could make is I say, okay, I'm summing over all elements in A, but that would mean I would count twice an element here. So actually what I'm saying is that for each equivalence class, I'm picking one representative each time, right? And this one representative is just one coset. So AH, right? If there's another BH that actually is the same coset, I'm not counting that one. I'm only summing over the distinct cosets. So A tilde H, maybe, and A prime H, etc. And so what this does, I'm able to say, to give this statement on the cardinality of G, oh, and sorry, I called it S, but really it's just G, G here, where the cosets are the partitions, the elements of the partition. If the cardinality of G equals this, I can just say now that since we have a certain number of representatives, okay, we'll denote this number by n, okay. We suppose that since the group is finite, there must be a finite number of representatives. Then we can say this is actually n times, sorry, not the sum, but n times the cardinality of H. Do you guys see what happened here? What I said is that since each AH has the same cardinality as H, I'm able to basically transcribe this as a statement on the nature. So since the equivalence relation induces a partition, I'm able to say that each AH is just basically the cardinality of H with this lemma. So now I've just shown this. So the cardinality of G equals, so rather the cardinality of H divides the cardinality of G. And if you guys are interested, this number is actually the index of H and G. This is the number of cosets in the whole group G induced by multiplying on the left, right? So so what we have explored here is the concept of left cosets, but really the exact same thing applies to right cosets.
Real quick, why did we make the restriction that A was not in H?
So if we did not make that restriction, we made that restriction because if A belonged to H, in particular, that would mean that I would be able to say that A times capital H, well, that's just this all the set of elements. You're multiplying an element of H with an element of H, right? So you're considering basically the set. I'm rewriting the coset here. AH, where H belongs to capital H. But since H is a subgroup of G, right? We made this hypothesis when we described the cosets in the beginning. Since H is a subgroup of G, we are able to assert that by stability, AH also belongs to H. And so basically, the cardinality, so the set H is just the same as AH. I don't know if that clears it up. Maybe there's something.
Okay, so sorry.
Even if they are the same set, though, wouldn't the lemma still apply, just kind of trivially?
Yes, absolutely. I just put we can just put A belonging to G. I mean, I just made that claim to make it non-trivial, basically. But yes, A can belong to G. Yeah,
All right, thank you.
yeah, no problem, no problem. I hope that clears it up. So here we've basically proven Lagrange's theorem because now we have that the cardinality of H divides the cardinality of G. This is extremely powerful because we're able to give now a statement on what subgroups can be. So for example, if I don't know if I had group G, which had cardinality 5, what am I able to say about this? So I know that if H was a subgroup of G, and cardinality of H would have to divide 5, but we know that since 5 is prime, either cardinality of H equals 1 or cardinality of H equals 5. So the trivial group, right, this is pretty easily identifiable, and the cardinality of H equals 5, but then that's the whole group, right? Because if you have a subset and you have as many elements as this set containing it, then you're obviously the whole group, right? So what we're saying is that if, in general, if the cardinality of G is a prime number, and this is, I really like this statement, if the cardinality of G is a prime number, that must imply, well, first of all, that the only groups containing it are the trivial group and the group itself, and that in particular, G must be cyclic. So how can we see this? I'm going to give a quick little proof. So we know any element must have some order, right? So if I take an element G belonging to capital G, I know the order of G. If the order of G equals 1, well, then we're done because G equals E. But obviously, if we take a non-trivial G, right? So we're taking a G out of E, then that must imply that the order of G must be some other number, right? So for instance, okay, here it might be better actually if we introduce another lemma. Right, let's maybe introduce, sorry, I maybe went a little bit fast here. If the cardinality of G equals P, that implies G is cyclic. Let's just do quick lemma. Quick lemma is if I have a subgroup, right? So if I consider the cyclic group generated by G, so I have some group G. If the cyclic group generated by G, so that's a subgroup of G, right? You can just check it quickly. I mean, if you have two elements in the subgroup generated by G, and just G to the I, G to the minus J. That's just G to the I minus J, but then you're considering the fact that if the group is finite in particular, well, there must be finite order. And so this means that I minus J is still an element, right? So it still belongs to N. And in particular, you're still in the cyclic subgroup itself. So what this means is that the cardinality of G, the cyclic subgroup generated by G, actually divides the cardinality of the group. And so now we can continue. So what this means is that since the cardinality of G is directly related to the order of the set, right? So for example, let's see. Let's give a quick example. If I have G equals Z over 10Z, so same as the previous time, and we consider now the cyclic subgroup generated by 2, that means we're having all elements 0, 2, 4, 6, 8, etc., all the way up to, well, that's over, right? Since 10 equals 0. We're actually having, so the order of 2 is simply 5 here, and we can clearly see there are 5 elements. So actually the cardinality of this, more in general, the cardinality of the cyclic group generated by G, that's just the order of G. And in particular, this means that the order of G by Lagrange's theorem divides the cardinality of G. So let's quickly prove our lemma on cardinality of G equals P. Well, if the cardinality of G equals P, right, that means that since every element has non-finite order but also not equal to 1, if you're considering an element other than E, that must imply then that, right, so the order of G must be something between P, might be or equal, but it must be strictly greater than 1. that must imply that the order of G divides P, but since P is prime, that must imply the order of G equals P itself, and or equals 1, but we restricted ourselves to G minus the trivial element for the sake of, well, non-triviality, I guess. The order of G must be P, and so that must imply that the whole group itself is cyclic. Because remember, if the order of G equals P and you have P elements, that means that G, E, G, G squared, etc., all the way to G to the P minus 1. Well, that's P elements, but you're in a P element set, so that must mean that all the elements are basically some order of G, which ends the proof. G, it must be cyclic. Great. Let's see. Well, that's a lot about cosets, I guess. We still have one last thing to cover. So really, like, as I said, all these statements for left cosets, they applied for right cosets also. And we're going to see later on that sometimes the left cosets are equal to the right cosets, but that's under a certain condition. We're going to just begin with a little counting formula like this one. It's consequence. Well, later on when you'll study group theory, you might see the orbit stabilizer theorem. This is a kind of like smaller result that kind of is a corollary of that, but we'll prove it. It basically states that if I have a homomorphism, phi, from a group G to G prime, right? And the left cosets, well, we've seen there the fibers, so the pre-images of the left coset, sorry, of the kernel of phi. So let's see, the kernel of phi. The left cosets of that, if we look at, sorry, hold on a second. Yes. We had a lemma previously that kind of stated that in a proposition 5.13, so let's recall that quickly. Proposition 5.13 kind of said that I have a homomorphism G to G prime, 5AB, 5n with kernel of phi, well, it's some element, some set n, okay. If the 5a equals 5b, if and only if A inverse B belongs to n, right? And so in particular, we can rewrite this. Let me just quickly make the quick little lemma we used. If I can rewrite this as B belongs to A kernel of phi. So basically what we're looking at here is coset. And we remember kernel of phi is a subgroup of the group G. So actually we're looking at a coset of the group, the subgroup kernel of phi. And so what we can do is, if we consider now this map G, which sends elements of the group to some element in G prime, let's say 5G, right? Well, in particular, I can say that if I have two elements, right, which have the same image, so in particular, phi of A equals 5B, so I'm actually able to say that two elements in the arrival set, in the group, the codomain group, I'd say, if two elements have the same value, basically, and they're sent by some two elements, A and B, in the original group, I'm able to say that phi of A B inverse equals E, and that implies, obviously, like we said before, that A inverse B, or AB inverse, sorry, that's here, yeah, so B belongs to A times the kernel of phi. Okay, so we're able to give this statement on, so there's a bijective correspondence with the elements in the image. What does this kind of mean? So if we rewrite our set G, right, and we write as the kernel of phi, we're able to split the set into different cosets. So here, A kernel of phi, So this might be A1 kernel of phi, A2 kernel of phi, etc., etc. And so what this means is that, well, first of all, remember every A kernel of phi with B kernel of phi, well, okay, here they might be, if they're equal sets, well, that's great, but actually we were looking at the cardinality. We know they have equal cardinality. That's a great place to start. What does this mean? It basically means that if I'm looking at um, all elements which send to the same place in G prime, right? So if I'm looking at some element y, okay, just focus on that, some element y, we know it's getting sent by some element in the beginning group. So y here, and I have two elements here maybe, then this guy gives the same equivalence class over here, A2 kernel phi. And maybe this guy might give y tilde, might give the same equivalence class A1 kernel phi, etc. And what this does is basically, it says that every element here that sends to the same guy here, y tilde, well, we're basically kind of forgetting that they all get sent to y tilde. We're only considering one of these guys, right? We're considering one representative in the pre-image of y tilde. Okay. And so this is the same idea as in the previous hour where we talked about the equivalence relation induced by map, because now we're able to say that if we look at the image of phi, right? Well, actually the cardinality of the image of phi, that all the number of different elements, so, so we have 5 elements, okay, y prime, some other elements, well, it's directly proportional to the number of cosets of the kernel of phi. So the more cosets you have, the larger the image will become. So we can kind of guess that the image of phi would actually be equal to some elements, so I know some n times the kernel of phi. What does this mean? Well, so hold on, this is actually quite false. It should be the cardinality of G, and then we would divide that by the cardinality of the kernel of phi. So if we have the image of phi, and now you're looking at all the elements in G, right? By dividing by the kernel of phi, since each coset has the same number of elements, right? You could even say, if you're looking at some A, some particular A, you're actually dividing by A times the kernel of phi. That just, in general, since all the cardinalities are equal, we're just considering this guy. If I take the set A, G, and I'm removing the redundancy, so the redundant elements in the kernel, and I'm only considering one of them, that means I'm only looking at each element in the image, right? So imagine I have one guy here, well, I'm forgetting all the other ones. So I'm only looking at what this guy sends to y tilde, and this guy sends to y, for example, or this guy sends to y prime. But all the other elements in the left coset, by dividing by the cardinality of the kernel of phi, the whole group, I'm actually only considering the elements in the image. So what this means is that the image of phi equals the index of the kernel of phi in G. I hope I was clear enough. Maybe not. Just tell me if you guys have any questions. I'll be open to answer those. And that's kind of it on cosets. Actually, I have one last proposition, right? So this actually is really important when we're going to tackle quotient groups a bit later. If I have a subgroup H of a group G, right? And in particular, if the subgroup is normal, so I will denote it by this, so it's a closed triangle. So if H is a normal subgroup of G, H is a normal subgroup of G if and only if any left coset is also a right coset. So if AH, well, it's also a right coset. So actually saying that, wait, is this the correct statement? If only if every left coset is also a right coset. Actually, that's kind of strange. Okay, let's give the other proposition now. If H is normal, in particular, if H is normal in G, that implies that AH equals HA for every A belonging to G. So let's prove this. This is not very hard. In particular, if you guys have seen what a normal subgroup is, all it means is that you're a subgroup of G, but in particular, you're stable by conjugation with an element of G and even an element of H concretely. So if I have any element G in capital G, so I'm taking G inverse, I'm conjugating by an element in H, I'm still in the group H. That's a property only held by normal subgroups. And so if I have this property, in particular, that's G inverse equals some element H tilde, I don't know. I can rewrite this as, and I can take, okay, so let's do it properly. This is the lemma, and I'm taking an A belonging to G that's arbitrary. If I want to show that AH equals HA, well, if I take this A to be arbitrary, and I already know that H is a normal subgroup, I can just say, okay, I'm choosing A to be G, so I can say AH, A inverse belongs to capital H. So in particular, AH, A inverse equals some H tilde, AH equals H tilde A. And since we suppose that H and H tilde were two elements that did satisfy this relation, right? That AH, A inverse belong to H, and we took it arbitrarily. We can kind of conclude that this means that AH equals capital HA for any elements A belonging to capital G. This holds anytime because here this is true for every G and for every H, and G belonging to G and H belonging to H. Okay, so now we're going to go on to the more important aspect. I'm going to skip the part on restriction of a homomorphism to a subgroup and product groups because those I do not feel that crucial. I'm just going to talk about now mostly quotient groups. And actually, first I'm going to do a quick detour on modular arithmetic. All right. So I used a bit of notation before, so modular arithmetic. Let's see, modular arithmetic. I used a bit of notation before. I said that two elements were congruent modulo n, if they had the same remainder. So basically what this means is that A can be written, so B minus A is some multiple of n, right? So it's some multiple of n. What this means is that if I'm looking at this means simply that two elements have the same remainder modulo n if you're looking at it under Euclidean division, right? So this is kind of like division you do at a grocery store, basically. If A and B are integers, what we're looking at is that sorry, it's a bit late. Called congruence. Okay. It says do not. So exactly. So basically, being congruent, so two elements being congruent is actually also induces an equivalence relation. And actually, it even induces a coset if you're considering the subgroup, the group Z over NZ. Let's see why this is true. Let's suppose you have two elements. So let's draw a grid line. And you have two elements. So I have 0, and I imagine that, and all the way to maybe to some n. Now you're considering two elements with the same remainder. Right? So what this means is that when you're looking at their Euclidean division, they have the same remainder R. What this means is that basically A can be written as Qn plus R, and B can be written as Q tilde N plus the same R. And these two elements, they would be in the same relation. So obviously A is related to, so if we create the equivalence relation, A related to B, if only if they're congruent mod M, we're able to say that A is congruent to A. Well, that's obvious because A has the same remainder as A mod N, sorry, N. A is related to B, if only if B is related to A. Well, that's also pretty easy, right? I mean, if you're looking at here, it's just simply a consequence of here. Let's see, A equals so A equals Qn plus R, B equals some other Q tilde N plus R. If I'm rewriting this, I can just simply say A minus B equals Qn Q minus Q tilde times N, and multiplying by -1, whatever, B minus A equals Q minus Q tilde times N. And this kind of tells me, well, I can say now that B is simply some other remainder with the same R. I'm actually, sorry, I'm really, this is not great. I'm going to give this as an exercise. I don't think it's really that hard. If A is related to B and B is related to C, then it implies A is related to C. So being congruent definitely induces an equivalence relation. So you can think of it more abstractly as, okay, what does an equivalence relation mean? Well, I'm having the same property being shared by all integers modulo n, and in particular, yeah, you would define that equivalence relation. Let's see. I'm just going to actually, maybe it's getting a bit late. I'll continue on quotient groups. Right. Quotient groups, 10 quotient groups.
If you had any last things you wanted to say about modular arithmetic, this is a good time since we've got about a minute and a half left in this meeting. But if not, then we can end and reconvene in 10 minutes.
Yeah. Wait, are we having another break, I guess?
Yes.
Okay, yeah. Yeah, maybe I could say some more things, definitely. Well, first of all, one great fact is that if I have two elements, right, a modulo n, their sum. So if I have a, if these two represent some, okay, hold on, let me rewrite it better. If a equals b mod n, or something like, oh, this is not great. Let's rewrite it. If I have two elements with the same remainder, their sum will have the same remainder. And in particular, their products will also, so let's write that. So if a bar plus b bar equals some a plus b bar, that means simply that under the relation, if and only if same remainder, two elements, so this addition is well defined. What this means is that if A has this remainder R and B has remainder R, then A plus B also has remainder R. And in particular, this is also true for multiplication. So if A bar B bar has remainder R, then A B bar also does. So let's maybe try and explore this. If I have some element A, which has maybe remainder via addition modulo via, sorry, division. I'm just gonna finish. I'm gonna finish on a better note than we left off. So I'm just gonna finish the lecture by proving. So I'm sorry, I did not do all the sections we required, but I do want to prove this lemma, which is important. So I previously said that if the sum of two numbers with the same remainder, well, their respective sum, okay, so if we consider this number A, which represents a remainder, and B with a certain remainder, well, the remainder of their sum is simply the remainder of their sum is the sum of their remainders. Particular, so we're gonna prove this lemma, which proves another statement also. If A prime equals A and mod n, right? And B prime equals B mod n, that implies then that A prime plus B prime equals A plus B mod n. So we're going to start with the proof. So for this, we're going to assume that A prime, we're going to assume both of these are statements. So in particular, that means that A prime can be written as A plus n times R for some R, for some R. And B prime equals B plus ns for some other integer s. In particular, this simply means that A prime plus B prime equals A plus B, and then I can factor out n to say that it's R plus S. And so this means that obviously A prime plus B prime, well, if you see this as modulo n, it's equal to A plus B mod n, right? And similarly, if I write A prime B prime, given these two systems of equations, I have A plus nr times B plus ns, which equals, if I distribute everything, AB plus n times AS plus RB plus NRS, which, so you can just see this by distributing everything and factoring out the n at the right place. This means that A prime B prime equals AB mod n, justifying the other assertion that the remainder is also just the product of the remainders. Great. So we won't have time for quotient groups, but one more important thing is that we talked about the canonical surjection. So the canonical surjection, as we recall, sends set S to the set of its equivalence classes. So in particular, the representatives. So if I have an element A, I'm going to send it to A bar. What this means is I'm basically abbreviating the set under the equivalence relation twiddle, right? Twiddle, a subset of S cross S, which is an equivalence relation. And what I'm doing is I'm abbreviating the group S to only talk about the different kind of traits an object can have, right? So in the very beginning of the lecture, we showed like two objects have the same shape. Well, that's a certain equivalence class, and so I can basically partition everything. In particular, if psi is a map from S to S bar, I'm sending A to the equivalence class array. And so we can apply the same reasoning now. We may create a map psi from the set Z to Z over NZ. What does this mean? So we're sending basically a number A, and now we're sending it to this same number A, but we're looking at its equivalence class. But what's the equivalence relation, you may ask? So we're defining an equivalence relation under Z cross Z now. But what this equivalence relation will be, it will say that two numbers are linked if and only if they have the same remainder mod n, right? Previously, we showed that if two numbers have the same, so here A prime equals A mod n and B prime equals B mod n, I'm basically able to preserve the group-like structure here if I endow this with addition and this with modulo addition, right? So modular addition. I'm basically able to create now this canonical surjection, which is going to send every element to its respective element modulo n. So in particular, we would say modulo n by denoting this as what we've taken as modulo n. So we're looking at the remainder of A. We can say it's like some q n. Q is a some number, and n is the integer we're considering modulo, plus some remainder. So basically, we're sending this to R. It's really the same thing. We're sending it to the remainder modulo n. And this is a well-defined map, as are usually canonical surjections. So yeah, I think I'm going to wrap up the lecture here. So overall, we just had to do quotient groups and the first isomorphism theorem. I will leave that to another lecture probably. Yeah. Are there any questions?
I don't see any questions in that chat, but like I really wanted to thank you for this wonderful lecture, and we really appreciate your participation in our group.
Okay, thanks. That's really kind of you. Thanks.
Yeah, thank you.
And I think based on the activity for this timing, I think we will get back to our usual timing of 6 or 5 a.m. GMT. Just for those who are here to know that.
Yeah, it's okay, no problem.
Yeah.
No problem.
Thank you very
Okay.
much again, and
Thank you.
goodbye, everyone.
See you.